This is section 9.2, the central limit theorem for sample means. So in section 9.1, we started looking at the distribution of x bars by using simulations. Remember, we had the mother's height that we sampled from. And so in this section, we're going to be looking at how we can use the central limit theorem to give us a very good approximation for the sampling distribution of x bar. If you remember, in Chapter 7, we introduced the central limit theorem as it applied to sample proportions. Those were our p-hats and how they were distributed. It's going to be very similar. Our conditions are going to be slightly different. So let's just take a look to see what conditions need to be met before we can use the central limit theorem. The sample is collected randomly from a population, so this one's going to be the same. And the observations are independent of each other. This can happen with or without replacement. Condition 2 says that the sample size is large enough, okay? Or, and this is important, or the population from which you're sampling is normal. So a rule of thumb is that sample size is large enough means that your n, your sample, is greater than or equal to 25. So if your sample is not greater than or equal to 25, but it's coming from a population that's normal, that will still work. And then condition 3 is that the sample is collected, if the sample is collected without replacement, then your population size, n, must be at least 10 times bigger than the sample size. So we'll be checking this condition here. So if these conditions are met, then the sampling distribution for x bar, we can use the central limit theorem to find out that the sampling distribution, the shape will be approximately normal. The mean, or the center, will be at our population mean, which is mu, and the standard deviation of x bar we'll be able to calculate, and it will be called our standard error. It'll be sigma over the square root of n. Okay, and we'll discuss this a little bit further later on, that sometimes we don't know what our population standard deviation is. We don't know sigma. And so we use our sample standard deviation, which is S. Okay, so if we don't know sigma, we can still estimate our standard error by using S. And we'll talk about that in a little bit. So, the central limit theorem, when the conditions are met, says that our x bars are approximately normal. Okay, they're going to be centered at mu, that's our population mean, and their spread is going to be smaller than our population standard deviation, and we can calculate it. It'll be sigma over the square root of n. Okay, so some key features of our sampling distribution we're talking about. So we have our x bars, they're centered at mu, and then we can calculate all the rest of the stuff that we've been doing. Sigma over the square root of n, mu minus sigma over the square root of n, and so on and so forth. And so having the central limit theorem helps us with several things. We know what shape our distribution is. We're able to see where it's centered. And now we can know how often we expect to see a particular value. So we know the center, we're talking about it here. It's going to be centered at our population mean. And we know about our spread, which we can calculate, and that's our standard error. Okay, and then finally from this we're going to be able to make inferences about our population. So we'll be doing that in our next section. So Let's go ahead and compare the simulations that we ran in section 9.1 to the results of using the central limit theorem, and see that this is really true, that the central limit theorem does accurately predict what we would expect. So just a reminder of what we did in 9.1. We had 1,000 runs of a simulation. Our population was Mother's Heights. Our population mean was 62.5. Our population standard deviation was 2.4. In the first simulation we ran, we had n equals 10. So we had 10, a random sample of 10 mothers, and then we found X bar, and we did this 1,000 times, and we ended up with this simulated sampling distribution down here. And you can just look at it and see that the shape was approximately normal. And then right here are the summary statistics from the simulated sampling distribution. So before we can actually apply the central limit theorem, we need to check our 3 conditions. Our first condition, that we had simple random sampling and independence. This one was met. It says it in our paragraph. 2, was our sample greater than or equal to 25, or did it come from a normal population? So our sample was 10, sample size was 10. So it's not large enough, but it did come from a normal population, so we're still meeting that criteria. And finally, we don't know whether it was done with replacement or not, probably not. So we want to know that our population size is bigger than 10 times our sample size. So our sample size is 10. So 10 times 10, we're looking at 100. And our population was 1,375. So this one is also met. So we've met our 3 criteria to apply our central limit theorem. And so what does that tell us? It tells us that we expect that our sampling distribution of X bars are going to be approximately normal. They're going to be centered at our population mean, which is mu, and they're going to have a standard deviation that we can calculate. We call that our standard error. That's going to be sigma over the square root of n. So if we fill in our numbers, we have 62.5 as our population mean. 2.4 divided by the square root of n will give us our standard error. So this comes out to be normal 62.5, and this is 0.7589. 2.4 divided by the square root of 10. So let's confirm that this is what we saw in our simulation. And sure enough, when we simulated this, we found that it was centered at 62.5, and our standard deviation was 0.736. Our central limit theorem says that we expect our standard deviation to be 0.758. Those are pretty close. So, yes, the central limit theorem did accurately predict all 3 things: the shape, normal, the center, 62.5, and the spread, which was 0.76 or so. So very close. So let's look at our next simulation. We had done 3 of them. So in this one, same scenario, only this time our sampling size is n equals 25. So we can check our central limit theorem conditions of simple random sampling and independence. This is going to be the same. Now we have n equals 25, so our sample size is big enough, plus we have our population is still normal. And then our last one, we want to check that our N, our population size, is bigger than 10 times our sample size. And that is the 1375 is in fact greater than 250, 25 times 10. So yes, we can use the central limit theorem. The central limit theorem for our x bars says that it's going to be approximately normal. It's going to be centered at 62.5, our population mean, and we're going to be able to calculate the standard error. That's going to be 2.4 divided by the square root of our sample size, which was 25. So this comes out to be 0.48. And again, here's our simulated results. We can see that they were normal shape. They're centered at 62.438, so that's pretty close to what the central limit theorem told us. And the standard deviation of our simulated distribution was 0.45 or so, and we calculated using the central limit theorem of 0.48. So that's a pretty good match also. And again, yes, this is good. Our shape, our center, and our spread all good. So now we are on our third simulation. Again, same scenario. Now we have n equals 50. So it's good to just review. We've got our simple random sample and independence. Check. Our n is equal to 50, so that meets the n greater than 25 or from a normal population. So we've met that criteria. And third, we'll just check to make sure our population size is greater than 10 times n. And that is true. 1375 is going to be greater than or equal to 500. So check. We can use our central limit theorem. Okay, one last time. That means that we expect our x bars to be approximately normal. Centered at 62.5 and have a standard deviation that we calculate. When we calculate it, we call it the standard error of x bar. So it has kind of its own name. And we have to remember that anytime we're talking about the distribution of x bar, we're calculating its standard deviation. So that's going to be the 2.4 divided by the square root of 50. And that comes out to be 0.3394. 0.3394. So now we can verify that with our simulated results. Yes, that's a pretty good match. Yes, that's a pretty good match. And so, again, the central limit theorem accurately predict the shape, because we see the normal shape. Hard for me to draw it. The spread and the mean, the center. So to summarize, this worked for all of our simulations, the central limit theorem. I'm going to just focus on this for a second. As the precision increased, the precision increased as the sample size increased. So we noticed that the standard error that we calculated kept getting smaller and smaller as the sample size was increasing. So normally we wouldn't run a simulation or we wouldn't collect 1,000 X bars. What we would do is collect one sample and we'd collect one X bar. But because we know how the central limit theorem works, if we meet all the conditions, we can know what the distribution of that one X bar would look like. We know how it's the distribution of X bar is going to be centered at the population mean. We know it's spread. We know the shape. One other thing to take note of is that normally we wouldn't know the value of sigma. I mentioned that earlier. That's the population standard deviation. But it turns out, and we don't really prove it in this class, but it turns out that using the sample standard deviation, which we call S, okay, is a good estimate for the population standard deviation. Okay, so we're going to do an example. I had a little malfunction with the recording software, so some of my writing's on here already. But let me read this, number 6. The sources report that the weight of a full-term newborn baby have a mean of 7 pounds and a standard deviation of 0.6 pounds, and they are normally distributed. So that's telling us that we're talking about our population up here. And so we have a mean of 7 pounds. That's our population mean is mu is equal to 7. And our population standard deviation is equal to 0.6. Next, it asks us to draw the normal model for this population distribution. Be sure to include your mean plus or minus 1, 2, 3 standard deviations, as well as a title for your axis. So you can see that I've already drawn that on here. We have our axes, which is weight of newborn babies in pounds. It's centered at our population mean, which is which is 7. And then I've marked on our plus or minus 1 standard deviation. The next question here says, use the normal model for the population distribution to find the following. What's the probability that a randomly selected baby has a weight of 8 pounds? Okay, so you can see that up on my drawing up here, I have marked in where 8 pounds would be, and I'm shading in the region that they're talking about. What's the probability of selecting a baby out in this tail out here? In order to do a question like this, we need to standardize and find our z-score for 8. So we're going to calculate that. That's over here. That z is equal to 8, that's what we're observing, minus our mean, which is 7, over the standard deviation, which is 0.6. This comes out to be 1.67. So the same thing that it's asking, the probability of selecting a baby whose weight is greater than 8 pounds, is the same thing as seeing a z-score that's greater than 1.67. Now we can use our standard normal table to look this up. If we look up 1.67 on the table, we're going to be finding the region that is over here, right? What's less, because the table always tells us what's less. So we're going to use the 1 minus trick of 1.67. So we have 1 minus the value we look up, and we find out it's 0.0475. So that's about 4.75%. The probability of selecting a baby that weighs more than 8 pounds is 4.75%. Now, we are going to take a random sample of 100 babies. Okay, so you picture we have a random sample of 100 babies, and now we're going to talk about X bar. And so if we're taking a sample and we're talking about X bar, we want to know, can we use our central limit theorem? So let's check our conditions for the central limit theorem. 1, do we have simple random sampling and independence? So it does say we're taking a random sample. We're going to assume they're independent, so that one's met. We have n equals 100. plus we're taking it from a normally distributed population. So we needed to have an n greater than or equal to 25 or normal population. We have both of those things, so we've met this criteria. And if we don't have replacement, we need to know that n is greater than or equal to 10 times our n. So since our sample size is 100, 10 times 100 is equal to 1,000. But our population size, really our population is all babies. So n is all babies. And so certainly 1,000 is less than all the babies. So I'd say we've met 3 criteria. So now let's apply the central limit theorem. The central limit theorem is telling us that our x bar is going to be normally distributed, centered at mu, our population mean, and its standard deviation we're going to calculate. That's going to be that standard error formula. Okay, so let's put some numbers in here. So our mu is 7, and we're going to calculate our standard error. That's going to be 0.6 over the square root of 100, which is equal to 0.06. Okay, so now this question asks us to draw our normal model. That's the shape. Include the center and the spread specifically for this model. So we start with our axes, and we want to label our axes. We're not going to label it with weight this time because that's not what we're talking about. We're talking about the mean weight. This is a sampling distribution for the means. So you can put sample means. You can be more specific, sample mean weights. Okay? But it's really important that we're talking about the sample. It's still centered at 7, just as it was above, but now our spread is much smaller. So let me mark in some, if I can get my pen to work. One more, 6.82. Okay, let me see if I can draw a prettier normal model. Maybe. Kind of rough. Okay, so now we want to use the normal model for the sampling distribution to find the following probability. What's the probability that a sample has a mean weight? So here, being careful, we're talking about our x bar. What's the probability that we pull an x bar that's greater than 8 pounds? So let's shade in where that is on our normal model above. 8 pounds. Here I am, I'm over here looking, I'm at 7.18. Well, 8 pounds isn't even going to fit on my paper. It's going to be way out here somewhere. So what's the probability that we're picking an average, a sample mean, that's greater than 8? It's looking very close to 0 to me. So we'll just still go through the work so we can see how to do something like this. Here. So just like above, we want to find out our z. So our z, in this case, we're going to do our 8, observing 8, minus our mean, that was 7, over our standard deviation. That's always what we're putting down here, but be careful. The spread of our x bars is our standard error. So we're going to be using our calculated standard error down here. And then this number comes out to 16.67. And so you can look it up on the table if you want, but it's not going to be there. The probability of being greater than 16.67 is basically 0. Is very, very close to 0. So that's just a reminder of how our spread is really getting smaller when we're talking about the distribution of x bar. So that's the end of section 9.2.